Come on, computer, start recording. Looks like it's going. Okay. Let me get the right slide up. This really shouldn't take us that long, honestly.
Time was open.
We do have to start at polarity. We're going to start sort of going back to more math than vocabulary. Molarity is not a hard thing to calculate. It's very similar to Boyle's law, which is P1 equals P2 V2. But I mean, all this gram and periodic table stuff, none of this goes away. So you have 24.3 grams of salt. Okay, that's obviously going to go up here. Okay, how do you change from grams of salt to moles of salt? How do you get here? What's the missing thing? Right, and so how do you figure that out? Periodic table, where the chlorine is 35.45 and sodium's like 22.99, I think. I know when they add together, they add up to 58.44 grams. And in this case, I didn't like do all little cross outlines because I put this on the thing so that they could see it remotely. I wasn't trying to put it up here. And my screen has shifted to the left. How? Yeah, how did you? The whole thing. Oh, we also lost power. You lost power. Okay, I'll fix that once we get through. Unless it's really hard for you guys to see the stuff on the edge. So 24.3 divided by 58.44, and I'll round it to three numbers, gives me 0.416 moles of salt. Oh, people are asking, was there a curve on the CBA? We decided to use the star curve. So what's in Parent Portal is the adjusted grade. I did that this morning. I can't remember off the top of my head. I'd have to go. I have to go and look. I don't remember. All right, molarity. Can we go back? All molarity is basically how strong the solution is. The bigger the number, the stronger it is. That's basically what molarity is. But you're going to be using molar concentrations of a known stock solution, or possibly what you want your end solution to be, and you're going to figure out in liters or sometimes milliliters, because those interchange with this, how much did you have to start with, or how much did you have to dilute it to get to the proper concentration. That's pretty much it. It's not hard. It's just something new I need to show you how to do. So you have either very strong, which we call concentrated. A lot of times they're called stock solutions, the stuff that not in this stock room, but like we dilute it down so that students could be able to mix chemicals, which we haven't really done very much at all. We did it at the beginning of the year when you guys were doing the precipitates. If it's weaker, it's called dilute. Okay, so stronger is concentrated and dilute would be weaker. It either has more or, what the heck? Hello? Hello, you speak now. What the heck? I want to speak to a human. Yes. No, it's, I don't even use, okay, no, I don't even use them. I don't know why they're calling it, it's Express Scripts. It's not even a human being. It pisses me off so bad. All right, so, sorry, I mean, seriously, at least, I'm getting my soapbox here. So, it's how strong or how weak is the solution. And normally we are dissolving either a solid into a liquid. The liquid is almost always water. Or it could be two different liquids that are being combined to make a weaker solution. Molarity is abbreviated as a capital M with a line under it. I don't know why there's a line under it. This is the way it is. I'm sure there's a reason for it, but I don't know what it is. It's how many moles of your solute, which could be a solid or a liquid, could be a gas, are needed to make 1 liter of solution. It's how many moles per liter. Now, if you have just moles and liters, awesome. But if instead you have a certain number of grams of a solid, then you have to divide that by its molar mass, which is what we did with the opener for the salt. They're the same thing. Moles is taken by the amount of grams you have divided by its molar mass. Periodic table stuff, like the opener. That's why we did that. In order to calculate molarity, you have to divide it by liters, not milliliters. Now, if you're figuring out how much of a solution and you're doing a dilution, then it can be in milliliters. But molarity specifically should be in liters, and if it's in milliliters, you need to divide it by 1,000. If you forgot how to do that, that's somewhere further in the notes. I didn't pull out the paper. Is that today? No, that's the test review. Why not print out molarity for you guys? What's one I did? Oh, here it is. Too many things being done all at once. All right, we're going to go through a couple examples, and I'm going to show you how to do dilutions. So more, like I said, more on the math side. I just didn't put the answers on there because those aren't my papers. Those are actually the districts, the Youngmans. We have 2.5 moles of glucose. This is sugar, okay? And we're adding that to water to make 1.5 liters of a solution. We want to know how concentrated it is. And well, molarity, this really should have a line under it. That's bad of me. Is the number of moles, which is already in moles, awesome, divided by the liters, which is already in liters. You don't have to do anything extra. You just need to plug them in. So the molarity of my glucose is 2.5 moles divided by 1.5 liters. Push a couple buttons real quick in the calculator, and my molarity is 1.7. Yes, those should have lines underneath them, and I did not do that. That's my bad. We'll fix that. Then I'm going to show you one where it's not straightforward like this, where you have to convert. Because when you're calculating molarity, it has to be moles. If it's not moles and it's grams, you need to change that to moles, and it needs to be in liters. If it's not in liters, you need to change it to liters. This is just straightforward. Let me tell you to teach you guys pH. That's been horrible. Oh, I don't know how well your phones are going to be able to do. Oh, that's a different phones. I don't know what the calculator function is for droids anymore. So anyways, we have a saline salt-like solution. It's got 0.90 grams of salt. Now we have to do this first, okay? Because just like the opener, because the previous one was already in moles. I didn't do anything. But this is 0.90 grams. Well, we, in the opener, figured out that 1 mole of salt is 58.44 grams. That's its molar mass. So I'm going to use this for my number of moles. I got a problem here too. It's not in liters. So I need to divide the milliliters by 1,000 to change it to liters. Or you can just move the decimal 3 to the left. It's the same damn thing. Now I can do my problem. Now I could have done all of this in, like, I could have done this instead. I could have done 0.90 grams over 58.44. And then I would have divided that by, I could have done it all together, but I don't want to confuse you by putting division in division. So I just did them separately. When you now do the number of moles, I just cut off the unit. I shouldn't have done that either. Man, I was lazy when I built these. 0.0154 moles of salt divided by 0.1100 liters is going to equal a molar concentration of 0.14. And like I said, the larger this number, the stronger the solution is. When we deal with hydrochloric acid, I think the strongest I've ever seen is 12 molar. That'll hurt you bad if you get it on your skin. Most of the stuff that you guys do use, the things that you actually have done, of course, at the beginning of the year, have been very dilute. Probably the most dangerous thing I let you guys touch was the ammonia. Ammonia, at the beginning of the year, stuff that smells like cat pee, burns your eyes. Yeah. Well, then you weren't here. You weren't here when we did that lab in the back, huh? I put the ammonia in there?
Yeah.
Oh, that's right. I didn't let you touch it. That's why.
Oh, wait, you like that bottom thing?
Mhm.
Oh, yeah,
Right.
you did it yourself.
Dilution, yeah, because that's dangerous stuff. Actually, I think it was.
I am a dangerous person.
It's-
That's what you have to do.
I only think I had a couple of vials of it though too. So I couldn't put one at each station. All right, so y'all, shh, hush. This is similar to Boyle's law. Okay, Boyle's law said P1, which is pressure, times V1, Braden, y'all, shh, equals P2 times V2. It's like the same setup, but it's not pressure. It's the molar concentration of the first substance times its volume is going to equal the molar concentration of the second substance times its volume. Now, with this, your starting substance is normally called a stock solution. You get that from the stock room, hence stock solution. And then you're going to dilute it out for whatever you're going to use it for, whatever the purpose of it is. When you do this with acids, this was a safety rule, normally on safety tests in some way, shape, or form. You have the water in the beaker already, and then you add the acid to it. Don't do it the other way around. I have done that before. I ruined clothes before in the lab, because if you actually have the acid in the beaker and you put the water in it, do you know what happens? It doesn't, well, it can. I've never seen it actually like explode, like break the glass, but it's like putting water on a hot skillet, how it pops and it fizzes and it gets all over you. So you normally would not do this. Possibly if you go off to college, like I worked for Grad Lab, made all their stuff up. So I got to do this stuff all the time. I got autoclave things. I got all kinds of cool stuff. All right, example. I have 100 mils of a 0.40 molar solution of magnesium sulfate. Well, I'm preparing that, but it's coming from a stock solution that is 2 molars in concentration. I'm trying to figure out how much of this I'm going to need to be able to make this amount. So I actually know my 2s, and I do not know one of my 1s. So molar concentration of the stock is 2. I'm solving for how much of it I need. I don't know yet. My molar concentration of my new substance would be 0.4 molar concentration for 100 mils. Now, I can leave this in milliliters. When you're calculating molar concentration, it has to be liters. This is dilution. It's going to probably be in milliliters because that's how we measure with graduated cylinders. Very, very, very similar to Boyle's law. It's just not atmospheres, kilopascals. It's polarity. So I would multiply these, divide by this one, just like how you did in Boyle's law. And it comes out to be a total of 20 mils from that stock solution. And obviously technically it's not regular water that you're using out of the faucet. We use what's called deionized water, clean water, not stuff that you drink. If you drink deionized water, you will probably die. It takes all the electrolytes out of you, and you'll have horrible diarrhea, and you'll throw up. And if you keep drinking it, you're just going to dehydrate yourself even worse, and you'll have a heart attack and die. So you don't drink. I'm not talking about the water that you get for like baby bottles and stuff. That's distilled. It's not deionized. Deionized is dangerous. Distilled is just, it's clean. It doesn't have extra stuff in it that comes out of our faucets to help keep our city water clean. Things like chlorine, fluorine. What else they put in our water? Put all kinds of stuff in our water. Okay, now this is all that I'm going to show you how to do. There's really not much on this. I don't know what I'm on. Double check and make sure that everybody can see it.
When do you feel like off?
No, I get headaches. Let's see. For in here, now let me pause. Let me stop the recording here. Oh, I see you now. Let me stop the recording.